So welcome to this presentation on stochastic frontier analysis and other parametric approaches to efficiency and productivity analysis. I'll split the presentation in two parts, where in the first part I'm going to discuss the different parametric approaches and dig into some details about how to estimate stochastic frontiers and how to interpret stochastic frontier estimates of efficiencies. And then the second part, I'm going to discuss how we choose the functional form, what kind of distribution assumption is proper to make, and then we're going to discuss hypothesis testing in SFA models. And we're going to discuss a little bit of software also. So that's the plan, and let's get started. Okay, so SFA and other parametric approaches. As always, I want to remind you that what we are focusing in a lot of these lectures is sort of the very core of doing a benchmarking or efficiency analysis, namely how to estimate a model and how to measure performance relative to that model, whether we use DA or stochastic frontier or some other ways to estimate the technology. And that is just a small part of doing a real benchmarking study. A lot of steps come before that, and several steps come, some steps come after estimation of the model. And in reality, we circle through these different steps many times in a real benchmarking project. So just to remind you that we are sort of focusing on the core technical aspects of estimating technology. And these are also the step among all those steps. This is the step, the frontier benchmarking analysis. That's the step that is mostly described in the literature. Okay, so the plan is I'm first going to show you some of the parametric alternatives we have, and then we're going to talk briefly about some old deterministic frontiers, something about probabilistic frontiers, and then we move and spend the most part of this presentation on the stochastic frontiers. I'll go through at this step here how to formulate them and how to estimate them. And then in the second part of my presentation, I'm going to focusing on the functional forms for the cost and the production functions, and also what kind of assumptions is it reasonable to make about the inefficiency distribution. And we're going to talk about hypothesis testing. So we start now by talking about the alternatives. And as always, we have two problems in efficiency analysis or in benchmarking, namely how to estimate the technology and how to measure deviations from the efficient frontier of the technology. And the parametric approaches help us to estimate the technology, but the distance measures, the performance measures relative to the technology that we use are very similar to the ones we use in DA. So that's sort of the same. The parametric approaches make some additional assumptions about the structure. So we don't just assume that a cost function, for example, is increasing and convex. We assume specifically something about a linear cost function or linear production function, or linear, log linear, or maybe translog cost function. So production function. So we make some a priori assumptions so that we kind of know the relationship except for the value of some specific parameters. That has the implication that we can do with less data in theory than we can do in DA. Although many seems to think that you can do a DA with less data than the SFA, but part of the problem is that we don't really get a warning when we do a DA model whether we have included the right variables or not. The fact that it's a parametric model means that it's less flexible than the DA model, but the gains from that and some extra assumptions we make about the distribution of the noise term and the inefficiency term, the advantage of that is that we are better able to distinguish between noise and efficiency. So we're better at noise and efficiency separation. So that's the biggest advantage of the SFA model, which makes it more interesting to use if you have data with a lot of noise. So just to illustrate, in reality, we don't know what the relationship is between inputs represented here with a single input, namely cost, and outputs represented again here in terms of just one output. The only thing we know is that we have some firms represented by the black dots that have produced certain outputs, like here, with certain inputs, like here, okay? So the idea of this modeling is to somehow link these points so that we get an idea about the relationships between inputs and outputs. And here it's like a production function because we have inputs here and we have outputs here. And if we have these observations corresponding to the black dots, we could, in principle, estimate many different functions. The first idea would be to do like accountants would do some kind of linear regression. But we know that that will sort of fit in the middle of the points, and that doesn't really fit the economic concept of a production function because the production function is supposed to give the maximum output for given inputs. So ideally, we want to push that that line towards the frontier. So we might sort of make a shift so that it ends up in that green one up here. If that was totally parallel to this one here, we could call it corrected ordinary least square, which is one of the parametric approaches that has been suggested. We could also do the DA, which sort of sits piecewise linearly on top of there, but we could also try to do like an SFA, which would be it could be like this linear one here, but it just pushed further towards the. So it could be like between. It could be sort of sitting like here, but a little bit further to the top than an ordinary least square. So actually, we could think of this one as a linear stochastic frontier. It should probably be sitting a little bit higher up. But otherwise, it's still somewhat inside the cloud of data points, but it is closer to the frontier than an OLS is. I said that I referred to OLS before, but I actually haven't drawn an OLS in this picture here, I see. You could, of course, also go out and talk to engineers and management consultants and say, what is the maximum output you could get out of given inputs if you could get rid of all kind of old machinery and what do I know? So have a really fine-tune the production, then you might end up in this blue area here. That'll be like an engineering standard. But we normally don't measure towards that. Instead, we measure towards models based on real observations. So we do relative performance evaluation relative to actually observed productions instead of relative to an abstract ideal. Okay. We have these two classes of methods. We have 4 classes of methods depending on whether we use parametric or non-parametric or deterministic or stochastic models. And what we're going to focus on in this presentation is mainly over here. We're going to start though by also mentioning some of those, the parametric but deterministic models, which are models where we assume that any deviation from the model is due to inefficiency. At the same time, we have also restricted the structure of the relationship to be parametric, so linear, log linear, quadratic, or something in that of that sort. The stochastic frontier allows for stochasticity, so there might be noise in the data, and there might at the same time be inefficiency. So that's what we're going to focus on this one over here. As I mentioned before in some other presentations, SFA is preferable if you are concerned about noise separation, and you can live with a relatively more restricted mean structure, relationship between input and output, like the functions we draw. If you want a really flexible one, if you have very little clue upfront about what is the relationship between your potentially multiple input and multiple outputs, you might want to go with a DA model. And then you have to give up part of that noise separation. Okay. So just in summary, the advantage and disadvantage of DA. DA ignores noise in the data and the model, which is bad. It compensates, however, with a very flexible non-parametric structure, like the piecewise linear one. It invokes limited assumptions about the distribution of inefficiencies. Actually, it's only when we make some kind of a test that we perhaps assume that it is that inefficiencies have most of its mass close to zero, and then it sort of declines. And DA makes it a little bit more complicated to test. In the presentation on statistical analysis of DA models, I talked a lot about bootstrapping and those kind of techniques, which are slightly more complicated to perform than likelihood ratio tests, which is possible in Stochastic Frontier. The advantage of SFA is that it allows for noise in contrast to DA. However, it imposes restrictions on the structure of the relationship between input and output up front. It invokes some distributional assumptions about exactly we need like half normal or exponential inefficiency terms. And the gains from having these extra restrictions is that it's easier for us to test. We can basically use a likelihood ratio test from general statistical theory. So to illustrate the different parametric models in the simplest possible case of linear relationships, you might imagine that you have some points here marked by crosses. You'll do an OLS, and we might assume that it sits here. This is the line that minimizes the sums of the squared deviation. So the deviation or error term could be from here down to here. You square that, you do the same for this one, you do the same for this one, you do the same for this one, and then you sum all these squared deviations, and then you try to place your line in such a way that the sums of those squared deviations are as small as possible. The deterministic one is always sitting on top of all the observations because realized production must be feasible, and that means that they must be on the production process function or below. So it sits up here on the top. The SFA is also close to this deterministic frontier, but it is a little bit inside because we realize that it's okay that there are a few points above, because that might just be because of log or because of noise in the data. It might not be because of some super efficiency of that firm. So that's sort of the main picture to keep in your head. And what I'm going to do now is to talk something about alternative deterministic models and then move on to the stochastic frontier models. In this literature, once you talk about parametric models, it's important to distinguish between additive models and multiplicative models. So in additive models, the normal regression is that you have like output is a function of the input and also some parameters beta, which we're going to estimate, and then plus the noise term, which can be a positive or negative noise term. The deterministic one ignores the noise term, but it includes the inefficiency term, okay? And that's like a half normal. It's like the U can only be positive. That's the idea of it, as written down here. They're non-negative, while the noise terms are some symmetric distribution, like, for example, the normal distribution. And then the difference is that once you go to the stochastic frontier, you have both of those terms. So you have like a composite error term, which is the sum of normal noise and then inefficiency. So that'll be one way to describe it. It's quite common, though, when you work with these parametric models, that you actually work in logs. So instead, you take log of y is log of these inputs. And then if you take log of the exponential of v, then it just becomes plus v in the log specification. So that is quite common to use. It has some advantages. For example, heteroscedasticity can be reduced by taking the log of these relationships. So I want to, it can be sometimes be confusing when you look at it. You have to be clear whether you're working in the additive model or the multiplicative model. But on the other hand, it's very similar, because if you just take the logarithm of all the items in the multiplicative, you actually end up in the additive one. But we have to be careful once we go from these estimates of the U's and the U's and the V's, and we go to a measure of technical efficiency. Then we need to think about whether we're actually working with a multiplicative one, where inefficiency will just be the exponential of this minus U. That'll be like technical output, technical efficiency of the Shepherd type. will just be an estimate of this one here or this one down here. But if you have an additive model, we need to do it slightly differently, which I'll show. So once you come to, it's the same estimation, except that you take logarithms to begin with if you have this one over here. But once you come to the interpretation of the deviation terms, you need to think about whether you actually did a log in the estimation of the SFA or you didn't do a log in the estimation of SFA. So I wanted to emphasize that up front here. Deterministic frontiers. So basically it's a parametric model, but it assumes no noise in the data. It means that we have decided on the functional form, linear, log linear, quadratic, something like that. But we don't allow for noise in the data. So you can say to some extent that it has the drawbacks of the DA because it doesn't acknowledge noise, pure random events, but it doesn't have the advantage of having a very flexible structure. But it's an interesting starting point, and historically it's also the first type of frontier, parametric frontier models that was proposed. And I'm going to cover a few papers here, just to give you an idea of how to think of it. So you can assume, for example, that you have a Cobb-Douglas production function, like here, typical Cobb-Douglas structure. And then you have this the constant term first, and you have that now the inefficiency term here. And remember that exponential of something negative, that is going to be at the most 1, and then it's going to be declining as u increases. So you're sort of multiplying a factor here, and that is actually going to be the output, the Shepard output efficiency. You could take the logarithm of these, and then you basically have a linear function here. So this is the one we're going to estimate in the next slide. But just to comment on what I indicated, this one is going to be the Shepard output efficiency, because what is Shepard output efficiency? Sorry, Shepard output efficiency. It's the realized output divided by the model output. Okay, so Farrell is that's the model output divided by the realized one, but the Shepard turns things upside down. So that's the realized output divided by the model output. So that's going to be a number below 1, okay? Because we believe that the model output is going to be larger than the realized output. So the realized output, if you have data, is yi, and the model output is basically what you have up here. So that would be this one here. So that's the model output when you assume that people are fully efficient. And that's like the frontier, right? So assuming that u is 0, so this is 1, then you basically just have this term here. So if you take this one and divide by this one, you can also sort of divide it over. What you have left is really the exponential of minus u. So that is the realized, an estimate of the realized output divided by the model output. So therefore, when we want to estimate Shepard output efficiency, we just need to determine that factor here. Okay, so if we can find that value, we can use this one as the Shepard output efficiency. Now, how can we estimate these parameters? Assuming that we want a function that sits on top of the data, so all data points are below, and all the data. So then we basically need that the logarithm of y must be larger than equal to this one here, and we want to make these u terms, what we subtract, we want to make them as small as possible, because we want to have at least one of the. We want to have the line sitting as close as possible to the data points. And you could, there's many things you could minimize. You could minimize the deviation terms. So basically you're looking for a function such that the sum of the deviations between your function and the actual observations is as small as possible. So these u's are as small as possible. You can do that. And that's, from technically, that's an easy problem to solve, because really, this is just a linear programming problem. You need to find the betas, and you need to find the u's such that those linear constraints hold, and you have one constraint for each firm in the organization. So you can solve this linear programming problem easily. And so that was one proposal, and then it was actually shown later on that corresponds to maximum likelihood estimation if we believe that the underlying U terms are exponentially distributed. So if you believe that there is this structure, this Cobb-Douglas structure, and if you believe that you have exponential inefficiency, then this here is a good way to model the relationship, the production function. Some other people have proposed to use not just the absolute deviation from the model, but to find a model and then to measure the distance up to the points below, and then to square those differences, and then to minimize that sum of the squared differences. And that is accomplished by minimizing this here. This is now a quadratic programming problem, because we have a quadratic terms up here. But otherwise, it's also a perfectly nice mathematical program, and one that is easy to solve. And the cool thing is that this one corresponds also to a maximum likelihood estimator, namely if we assume that the deviations or the inefficiency terms are half normal. Okay, so before, if it's exponential, it's better to try to minimize this without the squared. If we believe that inefficiencies, these U terms are half normally distributed, it's better to try to minimize the U squared. One of the very first frontier models is this idea of just taking the OLS estimates and then just doing a parallel shift so that they're sitting on top of all the points. Okay. It turns out that that procedure can also be given an interpretation as a maximum likelihood estimation. Namely, if we assume that these inefficiency terms, the terms that brings the output down, that they are gamma distributed. So all these old methods actually come with some link to theory, to statistical theory, in the sense that we can believe that they are maximum likelihood estimates of the frontier, which is actually quite similar to some of the statistical theory that has been developed for DEA. We can also show that it is that the frontier we estimate with DEA is asymptotically a maximum likelihood estimator, and it is asymptotically approaching that. So it is to some extent a reasonable way to estimate stuff, and it's not that it's similar to some of the logic in the DA, except that now we don't have piecewise linear one, we just have linear ones in the logs, so we have a much more restricted functional form. This simple approach of taking an OLS and pushing it to the frontier so that all points are just below it. On one point, it's at the line, at the hyperplane. As I said, this corresponds to having gamma distributed inefficiencies and doing maximum likelihood estimation in that model. Technically, it's very simple, basically, because you do an OLS here, and then you observe that there's a point that has, you look for the one that has the maximum residual, which in this case is this firm here. It has the largest difference down here. So now what you're going to do is you're going to lift this one up here. So you take the OLS and you lift it up with M. So now you use this model M plus log. But for this to work, then we need to, in reality, we also have a residual, right? But then because you're adding this, then you also should subtract it to make this whole, to make a log y equal to the right-hand side. So that basically means that you can take this part here, or this part here, which will be log of the cols, and what you have left is the residual minus this maximum distance, which is now also the inefficiency term. So you can basically estimate the inefficiency term by the residual minus m. That will be the inefficiency term, because if you move it up here, now this guy over here, he gets if you move the line up here, then this guy, for example, his distance from here to here is now going to be m minus his original residual, which is actually this part here. Okay, so it's like the residual minus m that we use to estimate. It's the residual from the OLS minus the m, which was the largest residual. We use that to estimate the u term, and if you want the technical efficiency, because we use log, then you take exponential or minus that, and that gives you the technical efficiency of the Shepard type. Good. You can go and try these things, and I've made a small script here which you can try. You load the benchmarking package, you load some data. These are data from an old paper by Chance and others about school performance. You'll then construct the maximum, you do the OLS. You do the OLS here on the logs. You see the OLS results here with the summary. You can find the maximum residuals by taking maximum over the residuals here. And then you can construct the Coles model, the corrected ordinary least square, the one produced by parallel shift. You can also plot the lines as here. I plot both the original line and I plot the Coles line here. And you can then calculate, as I said, the technical efficiency, Shepard output technical efficiency by this term, the residual minus the maximum residual exponential of that. And then if you do that, you get this distribution of technical efficiencies. So here was the OLS and here's the Coles. There's another set of ideas is called probabilistic frontier. It's a little bit less, has a little bit less theory surrounding it. The idea is more sort of a practical approach. You could estimate a frontier, then you could eliminate a certain share of the points that are closest to the frontier, and then you could re-estimate that. So that has been a proposal just to try to find those that are doing really well, and then to get rid of a certain percentage of those, and then to re-estimate the model. The question, it's not obvious which share to remove, so that's one of the problems, and it seems a little bit ad hoc, I would say. But there's also in DA some ideas about you take a frontier, you peel off the first layer, and maybe you peel off the next layer, and then you use sort of, because to get some kind of a safety buffer, you kind of move in a little bit, so you're not so ambitious to trying to imitate the very, very best, but maybe the 10% best is what we would like to ask everyone to strive for. It has been used in a practical context. In Denmark, sometimes you lower the maximum output you expect with some amount, or you increase the cost target a little bit. And in Finland also, I think at some point in the regulation they used like 90% efficiency was considered to be fully efficient. So that was basically the target. So you kind of got a target which was a little bit inside the point. So there would be like 10% of the points was actually on the top of that function. So it can be like a pragmatic way of dealing with it, but it's much less theoretical than the other models we talked about. I know this was a fast coverage of this, but it's just to give you a little bit of the historical background for what we're talking about here. So now I want to talk instead about stochastic frontiers, which is sort of the king of this parametric class. And it was first suggested by Eigner and Lovell-Smith in 1977, and actually at the same time by Moyser and Van den Broek. You do this as before. You could take like the logs. If you have a Kappa-Douglas function, you could take the logs, so it look like here. And then the difference is that now we don't just have a noise term V, but we also have an inefficiency term. And the inefficiency term is half normal, and the noise term is normal. That was the initial model. What is important to note is that inefficiency, since we have production, inefficiency leads to lower production level, so we have to subtract the inefficiency term. If it's a cost function, if we have like cost, we're trying to explain with the outputs, like here you have cost up here and you have outputs here, then inefficiency will tend to bring you above best practice. So in a cost function estimation, we need to add u to this v here. So that's the structure. You're trying to estimate these parameters beta and the variance of the noise term and the variance of the noise term and the inefficiency term. You estimate them basically like you normally estimate in statistical models, namely using maximum likelihood principle. So we choose the parameters in such a way that the observed data is as plausible or as likely as possible. So basically the task of estimating a model is one of maximizing the likelihood function, and that can be done that's a numerical problem. You have to use numerical methods. You can't sort of give a closed form solution to this. So you have to use numerical methods, and different numerical methods use also different parameterization. So in our benchmarking package, we introduce two variables like the sigma squared, which is the sum of the inefficiency variance and the noise variance and the inefficiency variance. And we use another parameter lambda, which is the square root of the variance of the inefficiency divided by the variance of the noise term. So note, if I know sigma squared and lambda, so in that way I get I have two equations in two variables, so I can solve it. So I can come from sigma squared and lambda into the individual ones here. So it's just another way of describing it. Instead of trying to find sigma v squared and sigma u squared directly, we rather try to see if we can find what is sigma squared and what is lambda. It has to do with the way that we search this space of parameters. An earlier implementation, but for sure an equally good implementation, is in the Frontier package based on the original program of Tim Quelli. They use a slightly different parameterization. They use the same here, but instead of a lambda, they use a gamma, which is the inefficiency variance divided by the total variance. So their gamma is the share of, you can say, inefficiency as part of the total variance. One has to be a little bit careful because this is not really the variance of the inefficiency distribution. It is the variance of the normal, which is behind the half normal, right? So because in the half normal, you don't really go to both sides, you only go to one side. So the variance there is actually smaller than it is for the normal distribution. But we normally just express this as the variance of the inefficiency and the variance of the noise term. I'm going to focus mainly on this one here, this parameterization as we go along. So instead of seeing the sigma v squared and then sigma u squared, you'll sometimes just see the sigma squared and the lambda. Okay, so we're going to use maximum likelihood principle, which is, I mean, conceptually, it's an extremely elegant idea. You have to guess what model is holding in reality. So what's your best guess? Well, that is the model that has a big chance of generating the data that you have in your hands. Okay, so it's a very nice idea, the maximum likelihood, and it's also statistically important because we know that it is consistent. So as the data size increases, then the difference between what we estimate and what is the true underlying parameters, that will go to zero. And it's also asymptotically efficient in the sense that it has the smallest variance around the true asymptotically it has the smallest variance around the true values of these parameters. And the last thing which makes it nice to use maximum likelihood is that there's a general testing theory, namely likelihood ratio tests. And of course, the whole SFA idea is nice because we separate noise and inefficiency. But there are some drawbacks also. One is that we need to come up with a functional form to begin with, and we need to justify the distribution for the inefficiency a priori. And there's actually a third one I should have mentioned, that is that sometimes it's really hard to solve the maximization problem, and it might not converge. So it's not, I mean, the DA will always generate results. Sometimes we cannot make these SFA models converge. And that happens in particularly if there's a lot of noise, so that the inefficiency part kind of drowns in the general noise. So the idea of maximum likelihood estimation is explained a little bit here on this slide here. So the idea is to find the parameters values, that is the betas and the variances, to maximize the likelihood of observing what we have observed. So you basically, you have observed the y. You can say you have observed y, and then you say, okay, how likely is y? It's actually the x's and the y's, but let's just call it y as a common expression here. So you have your data. How likely, what is the probability of getting that data given that the parameters are beta? And then the likelihood is to look at this probability as a function of the beta. So if beta is here, there's very little chance that the probability of generating my data is low. If it's here, it's a little bit higher. And so you're basically looking for this function, the likelihood function, and then you're saying that, okay, here it's really high to observe what we have observed. So I'm going to guess that the parameters are probably, I'll never observe the parameters, but I'll guess that my guess best at the parameters are this beta hat. Okay. Now the question is how to find this point here, because it's not a nice it doesn't look very nice, this function. You don't have even a nice closed form solution that you can just calculate with. You need to somehow find a numerical way to move along this curve here and get to this peak here. And then that is when you get to the peak, you know which parameter values to choose. Of course, if we just have one parameter beta, we could draw it maybe, and then we could easily see it. We could eyeball where do we get the highest value. But in reality, we have many betas. So we have, for all the inputs, we have a beta if we're talking production function. So we have many parameters. We have the original weights on these different terms, input terms, and then we also have the two variances, or the lambda and the gamma, that we talked about before in the alternative parameterization. So we have many parameters. So we are doing an optimization of a function of in multidimensional space. So it is actually quite complicated. Anyway, the method we use is something called the Newton-Raphson methods, and it's described down here. Because basically what you're looking for the place where the derivative of the likelihood function is 0. So if you can make the derivative of the likelihood function, then you just need to find a way to find where the derivative of the likelihood function, where that crosses the x-axis, where that is 0. And this can be done by this procedure here. And instead of, it's basically something like you approximate the function, that you approximate this function, the derivative. You make like a linear approximation at a given point. Then you try to assume that holds sort of in the neighborhood of that point, and you assume if it holds more globally, where does that linear function hit the x-axis, and then that gives you the next starting point for your evaluations. I'll show that. I'll have another picture in the next slide that illustrates that better. But basically, we try iteratively to find the point where the derivative of likelihood is 0, as I said here. But using this procedure here, which involves derivatives, and also, as you can see, it involves second order derivatives. So if you have a really flat function, it's not only is this one going to be zero, but it's also the function is also going to be very flat when it crosses the x-axis, and that is what creates the problem. Let me illustrate that in an example here. So basically, if this here is my derivative of the likelihood function, and I start with this point here, then I can find the value of the derivative. I see that it is positive, and I'm seeking a place where it is zero, so I would like to find this point here. So what do I do? Well, I make a linear approximation here using first order Taylor approximation. That gives me this line here, and that crosses down here. So now I say, okay, that's my new guess. And then I say, okay, what if I try this point? I can now see that it doesn't quite give me zero, it gives me this level up here. So now I have a new point on the function. So here I can again do a linear approximation, and that will give me a new guess, xn2. And then I can again see that I haven't quite reached zero yet. So now I will try again to make a linear approximation to this. And then I get closer, but it might take forever to get really close. So therefore, this procedure is not an easy one to always use. It depends a lot on the curvature of this function here. So that's to give you an idea that we are sort of using a numerical procedure where we are sort of trying our way, trial and error, and we try to make improvements all the time. But it's not something that is guaranteed to converge in a finite number of steps, as linear programming is, and since linear programming is the basis of DA, we don't have that convergence problem in DA. One way to understand why it can be so complicated is to really think about what these error terms and inefficiency terms are doing. So I plotted here 5 different distributions of the combined terms, the v minus the u's. Okay, so here I assume first, in the first picture, that the variance of the u is 0, so there's basically no inefficiency. So I just get a normal distribution here. Okay, now I introduce a slight bit of inefficiency. Actually, the inefficiency term is sort of is a half normal, and here with this dashed line, I've indicated the distribution of this inefficiency. But that has to be added to this to my normal, or be subtracted from my normal distribution, and that means that the difference between this one and this one here ends up being a distribution. The composite error ends up having a distribution, which is this one here. So you see, it has shifted a little bit. So the mode of that distribution has shifted a little bit to the left, and furthermore, it has also the tail, the left tail is now becoming fatter. But it's not a big difference, and really you need to identify this difference between these two curves in order to be able to differentiate between noise and inefficiency. Because the only thing you might observe is this one, and you get like empirical observation from this one here, and now you have to see if you can split that up in a standard normal and some half normal. So it is not an easy task to do. If they're equally, if the variances of the two are equal, then it becomes easier. Joint distribution is shifted more to the left, and it is also having a fatter tail. So you can now see that you get fatter and fatter tails, and in this way you will be able to estimate the level of inefficiency in the different points. So that's basically by looking at, basically you have to look at the asymmetry of these composite error distributions. So not an easy, not necessarily an easy thing to do. It's also So as I said, you have to take a likelihood function, take the derivative of the likelihood function and try to maximize that. Now the problem is that the likelihood function is not a nice expression, and here's why. What we can, the combined term which we can observe is really, the only thing we can observe is the combined term. And what is that? That is the actual output minus the functional output, or the functional output minus the actual output. Okay, so that's the only thing we can observe, that difference between observation and model. And that is really the V minus U term. Okay, so if we want to base, we want to describe, we need the density of these U terms, these composite error terms. This is a random variable, and we need to find the density of that, and then we need to try to maximize, by choosing the parameters, to maximize the density of this one at this point up here. Okay, so let's take a look at this density of the epsilon term here. So the density of the V, because that's half normal with, no, that's normal with a mean 0, that is a relatively simple expression here. Okay, standard normal distribution with variance sigma V squared. The half normal is the same, except that we only use the positive part of it. So you see, I only use this part, and so I have kind of the same density, except that I have to multiply with 2 to get a mass of 1. Otherwise, I just have a mass of half. So now I need to take values from this distribution and subtract values from this distribution. And I need to figure out what the difference between V and U, what is the distribution of the difference between V and U. To find like the distribution of a sum of a random variable or a difference of random variable, we call that to do convolution. And basically, this is what I'm trying to describe down here. So if I want to find what is the probability of observing epsilon, well, that is the probability of observing U plus the probability that the V is epsilon plus U, because then when I take this V and I subtract U, then I just epsilon left. So I need to, so one way to get epsilon is that this one is U and then V is equal to epsilon plus U, because then the combined term becomes epsilon. But I can choose a lot of different U's, so I basically have to integrate over all the possible U's. So U could be 100, and then the other one, and if this one is 200, then this I need to take 200 plus 100, so that'll be 300. So if this one is 200 and this one is 100, then the V needs to be 300, because if I take 300 and subtract 100, then I get 200. Okay. But anyway, the U could be 100, it could be 200, it can be 100 and 102 and so on. So I need to try all of them, because that's all the events that will lead to my given composite error. And so I have to integrate from minus infinity to infinity this term here. So, but I do know, however, that the U term can never be negative, so I can also just do it from 0 to infinity. But you see, I have to integrate a function, which is the product of two functions like this. So good luck with that, so to speak. It's not a totally trivial thing to do. It's definitely not trivial. It takes it's possible, but it's cumbersome. And if you do that, you get a distribution density that looks like this here. So you have square root 2, square root pi sigma squared, and then you have the sort of like the normal expression you have also in the normal distribution. But the problem is you have this one here, which we don't even know how to describe with an explicit formula. This is the cumulative probabilities of a standard normal 0, 1 distribution taken at this point here. So the only way to determine this is this one has to be determined normally by numerical integration of functions like this with a similar form like this. So you have this one is this term and this term is this factor and this factor is fine. The problem is this factor here. So it's not a nice expression, okay? Because see here, we don't even have an explicit formula for the cumulative distribution. It is something we solve by integrating the standard normal distribution. Okay. That means also that if I want to maximize this for a single firm, that also I could, instead of doing this, I could maximize the logarithm of this, because logarithm is a monotonically totally increasing function. And if I take the logarithm of this, I get this one down here. But that's just the probability, or the log of the probability of observing for a given firm. Now you have many firms, so you basically have to take like the composite, the probability of the joint probability distribution of epsilon 1, epsilon 2, and epsilon up to epsilon n. Or if you take the log, so that will be the product of those density function. So if you take the logarithm of the product, you get the sum of the logarithms, and then so basically you get like a log, the sum of a lot of logs, the expressions like this. And that's what I have here. So basically, the log for the likelihood function for the whole data set looks like this. So this here is the expression that we're trying to maximize by choosing lambda, sigma squared, and all the parameters in our model. We choose the parameters, which in turn determines these epsilons. So even this one might look complicated, but actually these epsilons are in itself like differences between observations and what the model suggests. So you get this one, you get terms like if you take epsilon 1, that is really this term here. So as you can see, it soon become quite complicated, and if you insert the actual observed error terms, combined error terms into the model, you can now express the likelihood function like this one down here. It didn't make it any more beautiful, but that's what you have to try to maximize by choosing now sigma, lambda, and the betas. And that is the function I'm going to try to find the highest point on. So we want to maximize this, and this will give us the estimate of our parameters beta, sigma squared, and lambda. If you do that, however, then we get an estimate, of beta. And now the question is, how should we measure technical efficiency? Shepard output technical efficiency. We do know that is actual output divided by maximum expected output. And depending on whether you have a multiplicative form, now we get back to the multiplicative one. The multiplicative one was that you observed this one minus you had some error, and you might also you might also have some noise, but we ignore that because we basically want to get rid of that kind of uncertainty. So you can say that the actual output is estimated by this one, and the maximum output is estimated by this one, and therefore the technical efficiency measure that we will use is this one over here. Ideally, if we knew the U, we will use this one here. We'll come back to that because we don't really know what the U is. If we were to do it in the additive one, we don't multiply this expression, this exponential of the U. We subtract the U directly. So we will try to estimate it like this, which is similar to like 1 minus U divided by the functional value here, or the maximum expected output. So it's 1 minus the inefficiency divided by the maximum expected output. So these are the ones we are going to try to estimate. But as I said, it is complicated because we never observe the U terms. We observe the functional form, and then we have observed the actual points. And what we can observe is this composite error term, the noise minus the inefficiency. So the question is, how can we now guess what the inefficiency is for a given firm? We can never observe it. We can only observe the combination of inefficiency and noise for a given firm. And the traditional way of doing that is that we rely on conditional expectations. So we say, what is the expected value of the inefficiency terms given that we have observed the combined error and inefficiency terms of epsilon? And the expression for this is given here. Again, not a particularly nice expression, but it's the expression where epsilon star is the epsilon times lambda divided by sigma. If you want to do it in the, that's for the additive, that's what you would use in the additive framework here. If you're chasing this, and then you will basically substitute this U0 with this value here. If you are in the multiplicative model, what you need to estimate is the exponential of minus U0, and so instead what you can do is you have kind of two options. One option is, of course, you could estimate the U and then you could feed that in here, but it will actually be better because exponential is not a linear function. It's actually better to say what is the expected value of this inefficiency term given my composite error term. So you will actually put the exponential inside the expectation sign here, and then that will give me this expression here. Again, a complicated one. And here are the parameters that we're using in these expressions. So these are the estimates that the computer codes will generate, more or less. It will definitely generate this one here. And we can also, it will also generate this one here, fed into this one, formula up here, but I'll return to what we actually estimate. I want to make, before leaving this typical way of estimating, I want to make a few notes here. It's clearly a complicated formula, but what is equally important is it doesn't give simple incentives for the firms to improve. Imagine a regulatory context where you're rewarded for having a small value of U, small estimated inefficiency. Now, this inefficiency is estimated like this. So you basically need your composite error term, and then you need to multiply it with lambda divided by sigma, and then you need to feed it into this model here. So if you increase your slack, that what will happen if you introduce more on inefficiency, what will happen is that if you add like 1,000, or if you eat like 100 of the breads that you're producing, so this U is now minus 100, it's like a slack you introduce. That doesn't necessarily mean that the measurement of your slack is going from whatever it was to 100 more, because you feed. What will result is that the output will be changed, but then you feed it into this whole framework here, and we can get an idea about a little bit of an idea about it, because this one here is some number less than 1. And this one here is basically the epsilon times lambda divided by sigma. So what is going to happen is if I increase my inefficiency with a certain amount, then that's not going to show up directly in the inefficiency term, because the SFA kind of interpret this increase in the composite error term as partly due to inefficiency and partly due to noise. So it's kind of forgiving me the part of my extra slack, because it just says that that's probably he has a big deviation, but that's probably because he was unlucky. That's one way to think of it. So that's an important point. And when we come to the incentive presentation on incentives and contracting and DA and SFA, I'm going to show you some of that because it has the implication that for some levels of performance, if you're having really low slack, low inefficiency, you have absolutely no incentive, or you have very, very little incentive to try to reduce your slack further. You might also increase it, and there will be little penalty in terms of a higher estimated inefficiency. But if you have more inefficiencies, it's a more one-to-one relationship. It's not a one-to-one relationship, but it's a more there's more power in the incentive scheme based on the efficiency SFA efficiency score. But it's a lot of details you need to understand before we get to that. But the intuition that if I increase my slack, my inefficiency, that will lead to the model interpreting my observation as composed of more slack or more inefficiency, but also more noise. It kind of explains why the model is to some extent forgiving or why the incentive powers is heavily reduced in SFA-based contracts. There's actually another way that you could try to estimate the technology. You could, instead of using the expected value, you could say that I want to use the mode estimator. So the mode estimator is the it's basically what is the most likely value of the parameters. Instead of let me put it differently. It is so basically you have what you have is that, okay, I'm talking too fast here. Okay, so what we did before is we never observe the use. We observe the composite error. So we're using the condition, we look at the conditional distribution of the inefficiency terms given the composite error, the composite epsilon here, which is noise and inefficiency. So instead of looking at the expected value of u, you could also look at the value of u where that gives the highest probability, which is the most likely u given that you have observed epsilon. Okay, instead of looking at the expected value of v given that you have observed epsilon, why don't you look at the u that has the highest probability, which is like the mode of the distribution. If looking at the conditional distribution of u given epsilon, what is the mode of that distribution? And that would be like called a mode estimator. So basically it will mean, and one can show that this is really the mode of u given epsilon, that is this mu star, which is calculated down here. This means that if you estimate it like this, it means that you will never, you don't believe that if you are sitting above the estimated frontier, you will be classified as having zero inefficiency. If you're sitting below, you'll be classified as having some inefficiency, but you can actually now be fully efficient in this model. So all those points that are sitting above, they will now be classified as being fully efficient. And we can also look at this mode here. It's actually just the composite error term multiplied by gamma, which is some number less than 1. So it is relatively straightforward in terms of incentives. If I increase my slack or my inefficiency, that means that the estimated value will increase. If I increase that with 1,000, then the estimated value will increase with gamma times 1,000. Okay, and that gamma is some number less than 1. So it will not show up entirely as increased. The model will not acknowledge all my extra slack, but it will always acknowledge a fixed share of my extra slack. So if I spend $100 extra, maybe it will, if gamma is 1/2, then it will say that, okay, we estimate that he has introduced $50 extra of slack, and then you can penalize me for that. But realizing that it is always only estimating like half of the slack addition, you can just say that you'll just penalize me for 2 times the estimated slack addition. So then you're sort of back to being able to penalize me 1-to-1. So from a incentive point of view, this mode estimation is actually a nice way to estimate in the SFA model. Just to close, I want to say a little bit about in the benchmarking package, how do you do all these things? Well, there's an SFA code, which I haven't mentioned here because that's straightforward. It's called SFA, and then you say input and output. And if you want to do logarithmic log transform, you just write log x, log y. Just remember that you're using that. So basically, you're using a multiplicative model. And then if you want to estimate the efficiency in the multiplicative model, which was this expected value of the exponential of minus u, then you use this function, which is called technical efficiency bc.sfa, and then you write the SFA, the result of the SFA estimation in here. This function is actually we call it BC because it's Baptiste-Quelli that proposed that way of doing it. If you wanted to use the mode instead, you can use this TE mode.sfa. And here I refer to the formula in the books, in the book DA, SFA, and R. And here, if you do the additive thing and you want to do the conditional, we also have a function for that. It's called TE additive SFA. And then you take that function on the estimated SFA model. I don't think we have, as far as I can see, we haven't defined the mode technical efficiency, the mode-based technical efficiency in the SFA package. But here I describe how you can do that. You can introduce a variable called mu star, which is the residual from the SFA, multiplied by this lambda 1 divided by lambda squared. And then you can take the mode, you can define a new one, which is mode additive, which is maximum of 0 and this mu star. And then you can estimate the additive technical efficiency Shepard output. You can estimate that as 1 minus this mode estimate divided by the fitted value according to the model value, the model's expected output. Okay. So you can easily write a few extra lines and then you get even a mode-based estimate of inefficiency in the additive model. And here I do show how all of this works if you just work with logs here. So it's a data set with milk producers. Here I have log inputs, log outputs, and here's the Baptiste-Quelli estimator, and here's the mode estimator. And if you do that, you can compare them, and you can also try to do just the Farrell output and the Shepard output. So ignoring the or using DA, you can get those estimates, and you can. We also here is how you do the Colt estimator, and then you can of course compare them all. What you will see here is that it doesn't matter that much whether you use the Baptiste-Quelli in this data set, or you use the so that is the expected value, or you use the mode estimator. It gives somewhat the same. You see that the efficiency is a little bit higher than what you get in the Shepard, in the DA model. You get a little bit lower, but the one where you get the lowest distribution of efficiencies. So the company looks the least efficient is in the Colt model, which is not surprising because it's sort of the most extreme one where you locate your function on the frontier. No point is beating the frontier. So you can take a look at that, but you see also at least they are positively correlated, the mode and the Baptiste-Quelli expected U estimator, that's it's quite similar, highly correlated. So this is just to give you a feeling for how these different estimators would work. A final note before taking a break and moving on to the second part of the presentation is about cost functions. All that I talked about so far is production functions. So I talked about estimating production functions where you have inputs that produce one output. A cost function you could also do. We do actually now have, there's one procedure that will estimate the cost function, but you can also just think of it, and it is actually what this extra procedure, SFA cost, I think it's called, is doing. But the idea is actually very simple. You just have a cost function is cost is equal to some function of output, and then plus a noise term. And now inefficiency is going to be added to the noise term because inefficiency increases cost. But if you took this cost function and you multiply it through with a minus, then you get minus x equal to this one is equal to minus v minus u. So now this minus u looks like in a production function. A v term is symmetric around zero, so it doesn't really matter whether you add it or you subtract it. And so what you have now is actually a production function where you consider this one minus x to be the output and this y thing to be the input. So if you want to do it with a normal SFA routine that can estimate production functions, then you can also estimate cost functions by just taking minus the input and putting into the procedure as an output, and minus the outputs and put them as inputs in the model. You just switch around those things, change the signs, and then do an exchange of inputs and outputs, and then you can use a production function procedure to estimate a cost function. But as I said, I think the most recent version of our package implemented this cost function. You can also estimate situations where you have multiple inputs and outputs. And maybe I should mention that. No, I think I mentioned that later. I want to mention a few more things. Sometimes you have panel data, and if you have panel data, you might want to impose some structure on that, where, for example, you assume that the inefficiency terms is sort of firm specific. It doesn't change over time, so it's time invariant. You can also assume that for a given firm, you have an efficiency term, but that is developing systematically over time. So, for example, it's developing like with a factor eta times t minus 1. So depending on the value of eta, it goes down, it goes up over time, the inefficiency term. It was originally called, in the Frontier package, it was originally called model number 1 in the Coeli version. I'm not quite sure if it's called that in the R package. Another cool thing you can do with SFA is that you can assume that the inefficiency term has a mean. So it doesn't necessarily just have to be like zero, like half normal. It could be truncated normal. So basically you take a normal distribution located anywhere, and then you truncate it by removing all the negative values. That's a truncated normal distribution. And the cool thing is that the mean of that underlying normal distribution could be a linear function of some other variables, some C variables, which could be explanatory variables. So, for example, you might say that what's the level of experience of the CEO? Can that help explain the efficiency? Well, you can model that, which you will in a DA context, you normally handle via second stage analysis. But here you can model it directly into the first stage by saying that you have that the mean of the inefficiency distribution is a linear function of such variables. So it's for example, linear function of the experience of the CEO and some other variables, the education level of the labor force, or whatever might contribute to having a more or less inefficiency in your model. So that's kind of a cool way to include other variables. It could also be, does it have to do with the quality of the products being produced or something like that? So that's a cool way to integrate other variables into the model by letting it affect the mean value of the inefficiency distribution. So we don't need to do some ad hoc two-stage analysis. And we can also test the importance of these factors, basically test whether these factors are significant. Okay. I think we'll stop here, take a short break, and then the next set of the last part of this introduction to SFA models will discuss the distribution and functional forms and some testing things. But let's take a break here, and then we will